Record. Okay, so we're very pleased today to welcome Nick Cowan to give us our seminar. He was an undergraduate at McGill, then went to do his PhD in Washington, was postdoc at Northwestern before making the transition to faculty, first at Amherst, and then in 2015 he moved back to McGill. He currently holds a CIC chair in planetary climate, and he's going to tell us today about the atmospheres of hot planets. Okay, oh, and I should say, he is happy to be interrupted during the talk. Okay, thanks, Nick.
You're muted.
Okay, I'm going to unmute myself and then share screen. This will work better. And I'm going to shrink all the little faces. Okay, there we go. Yeah, so my talk today is atmospheres of hot planets. So let's get to it. So all the work I'm going to present was done by my research group, not really by me, but I read the papers and write grants and stuff. So the McGill Exoplanet Characterization Alliance, that's our goofy name for our team. And basically it's a bunch of graduate students and undergrads in two different departments, mostly the Earth and Planetary Sciences department here at McGill and the physics department, because I'm in both of those departments. So here's a list of names, and I think one thing I should have added, but I'll give some shout outs during my talk, is that I work with a lot of undergrads, mostly from McGill for obvious reasons, from a variety of different departments here, but I've actually worked with two exceptionally good undergraduate students from Waterloo, and so I'll give them some shout outs as I go along in my talk. Okay, so I'm going to talk about hot planets, and the first thing to know is that all planets are hot when they first form, and that's true basically by definition, because you're smashing together objects from far away. They have a lot of gravitational potential energy, convert it into kinetic energy, and when they smash together, they turn it into thermal energy. So all planets start off hot, and the thing that you might not know is that many planets actually basically stay hot forever after that. And that's because they orbit close to their stars. So here is kind of a sketch of the planets in our solar system. You can see, how far they are from the sun, our star, and how big they are. And if you're worried about Pluto, I excluded it because it fell off the bottom of this plot, not because I care one way or the other whether it's a planet. And starting in the early 90s, first was with pulsar planets in 92, and then with radial velocity planets in 95. Astronomers started discovering planets in this kind of zone where in the solar system, there don't seem to be any planets. Okay, so these are what you might call a short period planet. So planets that orbit faster than Mercury, faster than the fleet-footed god. So as of whenever I made this plot, or whenever the database it's based on was updated, we already had thousands of planets, and most of the planets that we find are interior to Mercury's orbit. Okay, they have very short orbital periods, ranging from hours to days to weeks. And so those planets are going to be understandably hot just because they're orbiting close to their star. And in some cases, these planets are almost as hot now as they were the day they formed. Okay, so that's great. Nature can make short period planets. Today, I'm going to talk about 2 and hopefully 3, but we'll see how we go, of these planets. By the way, I can't see any of your faces or your hands or whatever. So if any of you have questions, just, you can ask the question. That'll be easier. So, so the first kind of planet I'm going to talk about, which I'll use as sort of an introduction to the tools of the trade, will be hot Jupiters. Then I will talk about lava planets, and time permitting, I will talk about M-Earths, which are basically earthy planets orbiting M-dwarfs. Okay, so we're going to start with hot Jupiters, which most of you will have heard of. They're basically just like Jupiter, except they orbit close to their star, so that makes them really hot. And so the specific science question that we're going to think about here is, how do hot Jupiters absorb and transport energy? Okay, so essentially, very roughly speaking, you can think of a planet as like a Carnot engine, where you're taking high-grade photons from your star, and you're doing some mechanical work and moving things about, and then ultimately you're getting rid of low-grade infrared photons to space. And there's, is basically a thermodynamics problem to zeroth order, and then in detail it has an awful lot to do with radiative transfer and fluid dynamics. And so we're just going to ask this kind of big picture question: how do these planets absorb energy? How do they transport energy around? So before going any further, hot Jupiters, they're hot. How hot are they? To give you a perspective, they are about as hot as an oven you would use for blowing glass. So this is a picture of a little mini hot Jupiter that I kind of made myself a few years ago when I could travel. And the temperature inside of the oven is about 1300 Kelvin, which is basically the temperature of a typical hot Jupiter. All right, so it's not like insane hot, but it's hot enough for things to be different from the Earth, or frankly, any planet in the solar system. Okay, so now we want to know what real hot Jupiters are like, not just the little glass ball that I blew in the when I was in New Mexico. And so we're going to use a space telescope to do that. And really the workhorse for much of this work was the Spitzer Space Telescope, which of course is no longer functioning. But it was a great telescope for this because it was in the infrared, which is where the heat from these planets is radiating. And it was not in a low Earth orbit, it was in an Earth trailing orbit, which made it very thermally stable. So it was a great platform for studying exoplanets. And frankly, once the coolant ran out on Spitzer, there was frankly very little useful science you could do with it other than exoplanets. And so we sort of had the run of the roost for the last decade of Spitzer, and we got to use it to do all sorts of cool science because really there wasn't much else that Spitzer could do at the time. Okay, so specifically, what kind of tricks did we do with Spitzer observing exoplanets? So most of you will have heard of transits. That's when a planet passes in front of a star. Some of you will have also heard of eclipses, which is when a planet passes behind the star. And that's a really useful moment. So during an eclipse, because the planet is going to slide behind the star, you're going to go from seeing the combined light of the planet and the star. And then for a brief moment, in practice, this is like a few hours long, but we've sped it up so you don't all fall asleep. The planet disappears from view and then it reappears from view. So what you end up getting looks suspiciously like a transit light curve, but it's not. This is what you're seeing here is not blocked starlight. You're seeing blocked planetary light, which means the depth of that eclipse is telling you something about the day side brightness of the planet. If you do this with visible light, it's telling you something about the albedo of the planet, how reflective it is. If you do this in the thermal infrared, like we did with Spitzer, it's telling you basically how hot the day side of the planet is. Okay, so those are eclipses, but that only tells you about the day side of the planet, basically by definition. And so if you're more patient, you can wait for the planet to go the whole way around its star, right, to orbit around its star. And that's going to lead to phase variations. And so these phase variations for a hot Jupiter, fortunately, the orbit is quite short. It's a day or a few days long. And so you can basically convince ATTAC to give you that amount of telescope time. In the bad old days, they didn't. And so you had data like what's shown in this cartoon, where you see these observations, these kind of really spotty observations, and then someone very courageously fit a sinusoid through that. Okay, so the combination of the eclipses and phase curves are essentially telling you how bright different parts of the planet are. So you do this at a couple different wavelengths, or ideally you get a spectrum, but with Spitzer, we were doing photometry. So we really just measure this at a couple different wavelengths. And that's basically telling you the brightness temperature of the planet at different locations on the planet. And so a fairly straightforward question that has a not straightforward solution is, how do you go from those disparate measurements of brightness temperature to an estimate of the effective temperature of the planet, which is what we actually care about. We want to know essentially the bolometric flux being emitted by that planet. So this is a problem that I've worked on off and on for a while. here is kind of the latest and greatest, which, oh, and this is my first shout out to a Waterloo undergrad, Emily Pass, who's now a graduate student working with Dave Charbonneau at Harvard. So Emily did a summer project with me. And it was literally a summer project. By the end of the summer, she had submitted this paper, which is uncanny. And so basically what she was looking at was this problem of, you know, how do you combine a handful of brightness temperatures into an effective temperature? And because it's the cool thing to do these days, she used a Gaussian process to do this. Anyhow, this plot is sort of an example of what you get and how you can estimate uncertainties and account for even systematic uncertainties due to the fact that we have basically pretty spotty wavelength coverage with Spitzer photometry. Okay, so essentially you got your eclipses, you got phase curves, you do some voodoo Bayesian black magic to try and convert these brightness temperatures into effective temperatures. So now what you're essentially doing is building a really crappy temperature map of a planet. And so here's an example for this particular hot Jupiter, HD 189733b. It's about 20 parsecs away. We can make a really low resolution map, and we can see that there's a point on the night side, the temperatures are as low as 900 Kelvin, still pretty hot. It is a hot Jupiter after all. And the hottest point on the planet is about 1200 Kelvin. And that arrow is actually pointing where the hottest point is, which is slightly east of the substellar point, which basically means that even though this planet is tidally locked, there are winds blowing heat to the east, right? So to put that more clearly, if you were standing at the little black dot in the center of this diagram, the sun or this planet's star would always be directly overhead. And yet that's not the hottest point on the planet. The hottest point is to the east of that. And you know, if you presume this planet is tidally locked, then that tells you that there must be winds blowing to the east. And astronomers basically favor this hypothesis because frankly, it had been predicted. Even before these observations were taken, there had been a prediction that on a tidally locked hot Jupiter, the winds at the equator would blow to the east, unlike on Earth, where in the tropics, you have the trade winds that blow from east towards the west. Okay, I'm not going to talk more about that. If you're interested in winds and conservation of angular momentum, you can ask me about that at some point. Okay, so this all sounds good. I haven't shown you any raw data, and that's because the raw data usually look pretty bad. Okay, so what I'm showing you here is actually a very beautiful data set. Like these are good raw data in the top panel. And so if you look at that top panel, you see a bunch of wiggly things, and then you see kind of a big dip in the middle. I'm not sure if you can see my cursor, but anyhow, right here in the middle, that there's a big dip at orbital phase 0, and that's the transit. That's when the planet passed in front of the star. And then if you look carefully, you know what you're looking for. You might also notice on the right-hand side in the top right there, there's another dip, a smaller dip, and that's the eclipse. That's when the planet passed behind the star. So again, this is a really good data set. They don't ever get better than this, and they are very frequently much worse than this. Okay, but even this beautiful data set needs to be cleaned up. And essentially what that means is we model all the detector systematics. And that's what gives you the much more beautiful looking phase curve in the bottom. So this is work by my PhD student, Lisa. And so once you've cleaned it up, then you can very easily identify an eclipse, a transit, and then the other eclipse, which means we basically observed this planet for a little bit more than one orbit of the planet around its star. And then all the kind of subtle wiggles you see along the way are the phase variations. That has to do with going from seeing the relatively bright, hot day side of the planet near eclipse to seeing the relatively cool, dark night side of the planet near transit. Okay, so now I'm gonna go into my sort of moralizing about like how we should do this properly, because it turns out we've been doing this trying to characterize the atmospheres of exoplanets for basically 2 decades now. And so some of the things we are learning is that because the detectors and the telescopes were not designed to do this work, different teams will get different answers. And sometimes the same team will get different answers depending on how they analyze the data. Sometimes different teams can reanalyze the same data, sometimes they reanalyze different data, and anyhow, it's a bit of a hot mess. And so here are kind of my 3 rules about how to do this properly. And so rule number one is, for each data set you have, you should really try a variety of approaches when you're trying to reduce and analyze these data. So this is an example of the state of the art. This paper literally was published like a month ago. So essentially going from left to right. So each of these little panels is actually just, if you stare at one of these thumbnails, it's actually a little phase curve. It's a phase curve of a specific planet. It happens to have an eccentric orbit, which is why the transits and the eclipses look a little bit like the timing of them look weird. It's supposed to be like that. It's an eccentric planet. And now going from left towards the right, what you're seeing are all different models that one can use to for the detector systematics. So these are all just different like acronyms. You don't have to know any of them, but the point is, going from left to right, these are all different ways you can try and model out the weird things that the Spitzer IRAC detectors were doing at the time. And then going from top to bottom, these are different astrophysical assumptions you can make, all right? So you got your detector and your astrophysics. And then, here's our best model. It's got the best Bayesian information criterion. And the nice thing in this particular case is that if you look at this thumbnail, the one that's highlighted in red, and you compare it to the other thumbnails, they all look pretty much the same, which is fantastic. That basically means that this result is pretty robust. It means that regardless of exactly what decisions you make regarding the detector systematics or the astrophysical modeling, you get basically the same idea about what this planet looks like. And in this case, it's eccentric, so it's exhibiting seasons. It's exhibiting eccentricity seasons. And so we can basically agree on what the seasons look like on this planet. On the other hand, here's the same planet, but with a different at a different wavelength. Okay, so this is now a different channel on Spitzer. And what we see, again, the best solution is the one in the orange box. But what you notice is if you look at some of the other boxes, you're like, oh boy, like the whole shape of the little wiggly curve is completely different from one of these thumbnails to another. So that basically means that the details of like which decision you make regarding the model is going to completely impact your what you infer about the astrophysics of this planet, which is worrisome, right? Because until this paper, the gold standard, what most people did is they just picked one of these columns and one of these rows, and the way they made that choice was usually based on the thing their PhD supervisor told them to do. And it was just kind of like you inherited, like, I did my PhD at this university, therefore I prefer this certain detector systematics model, and that's what I apply to all of my data, and don't ever tell me that it's wrong. And that's the way everyone worked, right? Like including me, like the previous papers I did. So this was very sobering to realize that, okay, sometimes these assumptions don't matter so much, and sometimes they matter a lot. And this is a case where it matters a lot. So basically we can't say anything robustly about what the heck the planet is doing at this wavelength. Okay, rule number two, ideally, once you build a really powerful pipeline like the one I just showed you, where you can analyze the same planet in myriad different ways, you want to be applying that same pipeline to all of the planets that you observe. All right, so here's an example of this by Taylor Bell, who's a recent PhD student in my group. He's now a postdoc at NASA Ames. And so he basically applied this for all the previously published Spitzer phase curves of exoplanets. And he went back and basically reanalyzed them all using a homogeneous framework. And basically what he found is that in many cases, the published literature values were totally legit and robust. And in some cases, they were really weird and unreproducible and certainly outliers. So that's good to know. And then last but not least, ideally, you not only use the same pipeline for all the planets, you actually simultaneously analyze and reduce the data from all of the planets. Okay, so what I mean by simultaneously is that you use a hierarchical model, which basically allows you to simultaneously fit for the nature of the behavior of the detector, for example, and the specific behavior it had for each individual data set you observed. Okay, so that's an example related to kind of detector systematics, but you can also play the same game with the astrophysics. You can say that, like in this case, for example, on this plot, we say that we presume that there was some connection between the x-axis, which is an irradiation temperature, is basically like how hot the planet ought to be, just given dimensional analysis. And the y-axis is the actual measured dayside temperature of the planet, given Spitzer observations. And so we expect these two things to be related. They should be correlated in some positive way. Generally, planets that receive more flux should be hotter. And so we can actually encode that when we try and analyze these planets. So instead of interpreting each of these planets as like a unique snowflake in isolation, we can say, look, this planet is one of like 50 planets we've studied. And in general, there's this positive trend that planets that receive more flux tend to be hotter. We can actually encode that using a hierarchical model, so that then what ends up happening is you get the black data points here where all of your error bars shrink and everything kind of shrinks towards the trend line. And it's essentially the difference between making an isolated statement about a planet as if you had never observed any other hot Jupiter in your life, versus saying like, yeah, these are data of a hot Jupiter, but I've also looked at 49 other hot Jupiters, and so I have some idea of how they behave. And those are actually two slightly different, sort of Bayesian inference problems. Okay, I think, yeah, that was all.
Before you move on, this might, they all seem to be like 500 degrees lower. Is there any, what do we take from that?
Oh, you mean the difference between the x-axis and the y-axis?
Yeah.
Okay, that's because, the definition of a radiation temperature is the local equilibrium temperature at the substellar points. That's at that point where the star is directly overhead.
Oh, okay.
And so if you want to relate it to, say, like the equilibrium temperature, you multiply it by 2/3 to the 1/4 power, which basically gives you that number that you were just quoting.
I see. Okay, thanks.
Sorry, like, so basically, I think most astronomers have heard of equilibrium temperature, and equilibrium temperature is totally fine in the solar system, where you have planets like the Earth and Venus and Mars that all have pretty uniform temperatures around them. But on exoplanets, most of which are tidally locked, equilibrium temperature becomes horribly misleading, because sometimes the dayside temperature and the nightside temperature will differ by hundreds, if not thousands of degrees Kelvin. And so we try to move away from like the spherical cow approximation and be a little bit more clear, like, this is the x-axis here is literally the temperature at the substellar point, and all bets are off as you move away from there.
Okay, thanks.
Okay.
So I also ask something, sorry.
Yeah, sure, go ahead.
So in your hierarchical model, do you also, do you also assume that these systematics that you mentioned are described by some sort of like stationary process, and then do you like fit for like the parameters, like a power spectrum of that kind of like, systematic fluctuations? Like, is that how this works?
So for when we tried to use hierarchical modeling for detector systematics, that was essentially what we're doing. We were saying that like on each pixel, so the dominant source of systematics with Spitzer IRAC is intrapixel sensitivity variations. So basically, depending on where the photons fall within a pixel, they have a more or less chance of leading to basically current. And it's pretty intuitive. If the photons fall in the middle of the pixel, you do good. If they fall towards the edge of the pixel, you don't do so well. So your sensitivity drops towards the edge of a pixel. And so essentially there's sort of three approaches here. One, you can treat each planet in isolation and just you fit for this detector systematic completely independently from another planet. That's what most people do. Alternatively, and some people, including me, have previously tried this, you can assume that detector sensitivity map is unique and is in fact the same for all planets. But it turns out that doesn't do so well either, for reasons we don't fully understand. There's either some time variability in these systematics, or there's a brightness, like a flux dependence of it. And so then the third approach, which is what Dylan did, and I should have mentioned, Dylan Keating is another ex-PhD student who now works in computer vision for a startup in Montreal. And so what Dylan did here with the hierarchical approach was saying that the length scale and amplitude of these intrapixel sensitivity variations were common among all the observations taken with a certain channel on Spitzer, but the detailed maps might be a little bit different from one observation to the next. So that was his approach. So I think, I guess, Neil, in your parlance, that would be like a stationary process or something like that.
Right. Okay, cool. Thanks.
And it's fun to see you again. I think last time I saw you, we both were in Illinois, maybe.
Yeah, maybe.
Okay, so on to science. So what I was describing is sort of like, data analysis, like nuts and bolts. And I'm happy to see some of you are actually interested in that, because usually that's the boring part of the talk. So what kind of science can we do with this? Basically, going back to the overarching question of like, how does heat transport work on hot Jupiters? What we've realized is that hot Jupiters are actually more complicated than we kind of hoped they would be. So one of the things we discovered is that their night sides all seem to be the same temperature, or at least pretty damn close to being the same temperature, despite the fact that the day side temperatures vary by a factor of 3. The night sides are all basically the same temperature. And we think that's because the night sides are basically shrouded in clouds. And so what we're seeing is basically just a thermal emission from a cloud deck, and it's always the same temperature. This is a phenomenon known on Earth. On Earth, it's the FAT hypothesis, the fixed anvil temperature hypothesis. And this is true of tropical clouds on Earth, for example. One of the other things we've noticed is some weird, some planets that basically don't fit the usual mold. In general, the winds seem to blow towards the east, like the one example I showed you of that map. It looks like there's winds blowing towards the east. This had been predicted. It makes sense in terms of Rossby and Kelvin waves propagating on the planet. But we've seen, we saw one example in 2018 of a hotspot on the western side of the planet. And since then, there have been a few more reported. And so we don't know exactly what's causing this. The two leading hypotheses are either something about clouds again, but basically that the day side would be partially cloudy, and those clouds would basically obscure some flux of the planet and therefore shift the apparent brightest point on the planet to the west. Or it might have to do with magnetic fields, which, like in all areas of astrophysics, is the boogeyman for exoplanets. Exoplanets has two boogeymen, right? We have clouds, aerosols more generically, and we have magnetic fields. So we have an embarrassment of ways to explain away weird things that don't make sense.
Okay, so the aerosols are replacing dust for galaxies then.
Exactly. Well, yeah, and it's exactly, these aerosols are quite literally dust. They're silicate, they're often silicate clouds. So they're little grains of silicate that have just condensed out of vaporized silicate. Yeah. So magnetic fields, why the hell would magnetic fields matter? Well, the temperatures are so hot on these planets that the atmosphere is partially ionized. So you have ions and electrons floating about. So they're actually coupled, the atmosphere is coupled to the magnetic field, which means that as the wind tries to blow through the magnetic field, you're going to get drag. So that's going to slow down the winds, and you're also going to dissipate energy. And annoyingly, there's no guarantee you're going to dissipate that energy locally. You might dissipate that energy somewhere else along the magnetic field line. So there's a whole cottage industry of trying to couple what's going on in the atmosphere of a hot Jupiter and how that could help inject energy in the deep interior and possibly help inflate these planets, which is a long-standing problem. Like basically hot Jupiters are bigger than they ought to be. Okay, so magnetic fields, weird. Disequilibrium chemistry I won't talk about, but the last thing I'll mention is enhanced heat transport through molecular dissociation. So this is a fun idea that my student Taylor Bell and I worked out. Basically, the idea is these planets are hot enough that on the day side, you should have atomic hydrogen, and on the night side, you'll have molecular hydrogen. And this is all good and well, except that ripping apart hydrogen takes a lot of energy. And then recombining it releases a lot of energy. And so we realized and figured out sort of a semi-analytic way to calculate this, that this dissociation and recombination was going to behave suspiciously like latent heat from water vapor in Earth's atmosphere. So in Earth's atmosphere, about half of the heat transport is through latent heat rather than sensible heat. So it basically means instead of heating up a parcel of gas, moving it somewhere, having it cool down, you evaporate water, move it somewhere, have it condense. And turns out hot Jupiters do the same thing, but like in spades through this molecular dissociation process. And this is something that has subsequently been implemented into general circulation models. And we've actually empirically looked at phase curves that show evidence of this. Okay, so I hate to be the person who asks these grand questions and doesn't try to answer them. So let me give you a 0th order answer to how hot Jupiters absorb and transport energy. How do they absorb energy? Pretty well. The bond albedos of hot Jupiters range from about 3% is the lowest, and the highest one is about 30%. We don't clearly understand why there's a range of a factor of 10, but there is. Okay, so that's the energy that gets reflected away. Where does the absorbed energy get absorbed? It gets deposited at a pressure of about a few bar. So the Earth, like at the surface of the Earth, we're at a pressure of 1 bar. So that means the light from the stars is being deposited, a little bit deeper in the atmosphere than where the surface of the Earth lies, but not that much deeper, right? So the pressures we're talking about are not insane pressures. So that's where the energy is deposited. And then because of these huge horizontal temperature gradients, because basically the day side tends to be much hotter than the night side, that leads to winds of a few kilometers per second, which is on order of the sound speed. Okay, so the winds are sort of transonic to supersonic on these planets. And we don't know exactly what governs the wind speeds either. These are all kind of 0th order statements. I can't tell you how these vary with planetary mass, planetary metallicity, orbital period, or really anything. We literally don't know. So hopefully by observing lots of more planets, either with James Webb or a mission I'll mention later called Ariel, we're hoping to sort out at least the 1st order effects, to go from 0th order to 1st order effects.
So for our Jupiter, is the albedo like similar or is it much larger?
Oh, our Jupiter? Our Jupiter would be at the higher end of this range. Yeah, and most planets in the solar system are more in the tens of percent. So like the Earth is 30%, right? Yeah, most planets that have clouds and things tend to be in the tens of percent range, 30, 40% albedo. Some planets like Venus is up at like 70 or 80% albedo. Really the weirder ones to explain is the 3% albedo. That's darker than a charcoal briquette. Which basically means not so much that the planet has no clouds, it probably means that the planet, it might have clouds or who knows, but the important thing is that it has optical absorbers. So it has things in its atmosphere that actively absorb shortwave light from the star. So that could be, alkali, like sodium and potassium, things that are pressure brought in that will just kind of give you really broad absorption across the optical, or it could have to do with the kinds of aerosols on these planets, right? If you have planets with weird aerosols. And to be clear, these are all weird aerosols. No one has ever really studied these clouds in any detail before. That's really one of the things we're hoping to do with James Webb, is to identify what the heck the clouds are actually made out of and what their optical properties are.
Okay. These hot Jupiters, then you're saying, do have these very complicated molecules, I guess, in their atmospheres, despite having these temperatures of like thousands of Kelvin.
I mean, complicated. It's not that the molecules are pretty simple, right? So you get things like iron oxide, aluminum oxide, silicate. These are all very refractory things that are happy to be there. You're not going to get like a hydrocarbon. That's not going to be stable at these temperatures. The thing that's complicated is when you start making aerosols, and the question of like how big the aerosol is and what its shape is and how porous it is and stuff like that. That's what's hard. I mean, to be frank, that shit's hard on Earth with water vapor that condenses, right? Like clouds is like the #1 source of uncertainty for like IPCC predictions about climate change on Earth. And so maybe it's not surprising that when we go to more exotic clouds, we're really uncertain about what's going on.
Great, thanks.
Okay, on to part 2, lava planets. So a lava planet is also really hot. That's the theme today, right? Hot planets, hot atmospheres. And the day side is, something like 2,000 or 3,000 Kelvin. The only difference between a lava planet and a hot Jupiter is that a lava planet is small enough that we think, like in terms of its bulk density, it ought to be made out of rock. And hence we assume the rock is molten. And if you have molten rock at the surface of a planet, that's the definition of lava. So our big overarching question here is, do lava planets have atmospheres? So first, let's talk about some geometry. This image is not to scale exactly, but it's close to being to scale. So I've made the planet look bigger just so you can see the different regions I'm going to talk about. But the angular size of the star as seen from the planet is actually accurate. Okay, so these lava planets orbit about 2 stellar radii away from the surface of the star. So that means 3 stellar radii away from the center of the star. So that means that if you were on a lava planet, as you all know from teaching astronomy 101, on Earth, if you want to block out the sun, you can hold an aspirin at arm's length, right? And that basically perfectly blocks out the sun, because the sun's about ½ a degree across. On a lava planet, your star is about 50 degrees across. So that's about the size of a yoga ball held at arm's length. So the star is really big in the sky, and that has interesting consequences. So that means that the day side, where the star is fully visible, is actually less than a hemisphere. The maximum temperature on the day side for a typical lava planet is something like 3000 K. Then there's a really broad twilight region that actually takes up a large fraction of the planet. These are regions where the star is partially visible, so where you're seeing essentially a sunset or a sunrise kind of a thing. Even in that twilight region, the temperatures are hot enough that you're going to at least partially melt the surface, about 1500 Kelvin. The night side is actually less than a hemisphere, and it can get quite cold. So we expect temperatures of about 100 Kelvin on the night side. So this leads to an interesting scenario, because the day side has this huge pool of magma, basically this molten rock. And you can't have molten rock at the surface of a planet without having some vapor above it, some rock vapor. Okay, this is the same way you can't have like a glass of water in your room without having a little bit of water vapor coming off of that. And so these are some simulations done by Zhang Wen, who's a grad student, not at McGill, but at York University, but I've been his sort of like adopted PhD supervisor for the last couple of years. These are calculations he did, hydrodynamic calculations of the what's going on in the atmosphere of these planets. And so on the left, you've got the substellar point. That's where it's the hottest, and the surface pressure, the pressure of the atmosphere is going to be the highest. Here there's 3 lines. Each of them is just for a different possible composition of the atmosphere. So sodium, silicon monoxide, silicon dioxide. And then as you move away from the substellar point towards the right, you see that the pressure basically drops, and it eventually drops very precipitously. So essentially what's happening is that you have a bunch of vapor on the day side, and yet the night side has literally no atmosphere. And so the vapor is going to try and move towards the night side. And as it does so, it's going to move faster and faster. It's a lot like a Parker wind or something like that for the astrophysicists. So it's actually going to go supersonic, and is going to adiabatically expand and cool. And so eventually, as it cools, the atmosphere is going to condense back into little rock grains, and it's going to snow back down onto the surface of the planet. Okay. And so the pressure drops basically to 0 when you get to the perpetually dark regions of the planet. And so here's the wind. As promised, the winds go really fast. They go to 1 or 2 kilometers per second, which is, if you look at the Mach numbers, is insane. It's like Mach numbers of 10 or 20 or 30. So the winds are going really fast. So it would suck to be on this planet, even if you're in a part of the planet where the surface was solid, so your feet weren't in like molten rock. You would get sandblasted by supersonic winds. Okay, so our cartoon of what this looks like is you have this magma ocean on the day side. You have basically a rock vapor wind blowing towards the night side. You're going to get rock rain at first, and then when you get farther closer to the night side, it comes down as snow. And then, of course, you're removing all this mass from the magma ocean, so that you can't keep doing that forever, and you keep depositing the mass like near the day-night terminator. So eventually there has to be some return flow, which is mostly in the form of a magma current. So it's basically the magma ocean is flowing the way the ocean flows on Earth. So it's actually not terribly different from like the water cycle on Earth, that like my son is learning about it right now in secondary 1, like evaporation, condensation, rain, little creeks, and going down into the ocean, and then evaporation and so forth. It's the same thing. It's just with rock. Okay, so what I just described was entirely thermodynamics and fluid dynamics. Okay, so I was basically solving Navier-Stokes in like a one-dimensional, basically column, like in the horizontal, or not a column, whatever that is, a slice in the horizontal. Turns out radiative transfer is interesting on these objects too. So this is a follow-up paper that Zhang Wen is doing with me. And basically, the key thing here is simply that silicon monoxide, which is our most likely candidate for what these atmospheres are made out of, is silicon monoxide. I can talk about why that is later if you're interested. But anyhow, so we think silicon monoxide is what the atmosphere is made out of. And the thing is, silicon monoxide is basically transparent in the optical, which makes, to some extent, makes the radiative transfer really easy. Like radiation from the star just goes right through the atmosphere and heats up the surface. And then because the surface gets warm, it evaporates. Okay, this is not terribly different from what's going on in Earth's tropics today, right? A lot of the energy from the sun makes it right through the atmosphere in the tropics, heats up the surface, evaporates water. Okay, like that's like to 0th order a good way of understanding tropical climate. So the same thing's happening on this planet. The problem is that silicon monoxide is actually very absorptive in the UV. Okay, and so you can see that in the blue part of this spectrum here. It is more absorptive in the UV than it is at any other wavelength. And so that's going to lead to temperature inversions. It basically means that some of the light from the star, which is some of the light from the stars in the ultraviolet, is going to get deposited high up in the atmosphere, the same way that the ozone layer ends up absorbing a lot of UV from the sun, right? And it leads to a temperature inversion in our stratosphere. So we're going to get the same thing on these lava planets. But it gets weirder because on these lava planets, the optical is fairly transparent, but so is the infrared, right? So their ability to radiate away heat, the ability of these silicon monoxide molecules to radiate away heat in the infrared is pretty crap. And so what that means is that it's absorbing a bunch of radiation in the UV, and it basically has no mechanism to radiate away energy. So this is actually a fairly common issue in, like interstellar medium, probably, and like solar corona. Like anyhow, it's an astrophysics problem that you've all probably heard of before. Is if you like heat up something that can't cool down, what happens is it basically gets really hot, and in particular, it gets so hot, it gets hot enough that it can start radiating away energy in the ultraviolet. And so that's what happens in the top panel is the same one I showed you earlier. The bottom panel now is the one to focus on. And look in particular at the solid black line, which is this top solid black line here. And the point is that the atmosphere will end up being basically the same temperature everywhere on the planet where there is an atmosphere. And it's going to be everywhere about 3000 Kelvin. And that's because once the atmosphere gets to about 3000 Kelvin, you get a tiny, tiny sliver of the vene tail of the black body radiation that peaks into the ultraviolet, and then it can finally get rid of its heat. So this planet is actually, the atmosphere is actually staying cool by UV radiation. So it's being both heated and cooled by UV radiation, which is a pretty trippy idea for a planetary atmosphere, in my opinion. Okay, so that's what's going on in the atmosphere. Basically, you have this balance of UV heating and cooling that's maintaining this atmosphere really hot. And we're hoping we can try and detect this with upcoming observations with Hubble and with the James Webb Space Telescope. Okay, so that's all the surface. What's going on underneath? So this is work by Charles-Édouard Boucaré, who goes by Shed, who's a postdoc actually in Paris, but fortunately for me, he lives a lot of the year in Montreal. And so we've gotten to collaborating on some fun geophysics problems. So he studies magma oceans, which is like the beginning state of all terrestrial planets. Because remember, all terrestrial planets start off really hot. They all start off molten. And so Shed, studies these magma oceans. And like most people, he usually studied them in kind of a spherical cow way. But then I told him about lava planets and he got really stoked because he was like, wait a minute, there's like a magma ocean where there's like thousands of Kelvin temperature difference from one place to the other in the horizontal direction. He's like, no one has ever thought of that for a magma ocean. No one's ever tried to model that. So he's in the process of putting the finishing touches on a numerical code that can actually do justice to this problem. And basically what we want to figure out is like, does this magma ocean even convect? Does it advect? Does it move around? It's basically a hot mess because parts of the magma ocean will be fully molten, which is relatively easy. It's just a fluid. Part of it is solid. That's also easy. It's a solid that also moves very, very slowly, like the way our mantle does. But then there's a middle part, which is partially molten. And that's where things get really dicey because the viscosity becomes very high. So it's still a fluid, but it's kind of like a slushy fluid. And also the composition of the liquid becomes very weird. Okay, and this is the same thing that happens like on Earth. When you get some partially frozen slush, for example, things like salt will preferentially want to be in the liquid form rather than in the ice. And so as you take slush and you gradually freeze it more and more, you get more and more concentrated brine. And so anyhow, we're trying to figure out what this is going to do to the atmospheres of these planets. So this will come out soon. Okay, so again, big questions. Do lava planets have atmospheres? Let me take a stab at the answer. Yes, they do on the day side. This is guaranteed, okay? And the reason I can say this with so much authority is not because we've actually observed like definitive signs that they have an atmosphere. It's just based on theory. It's like the day sides of these planets is hot enough that rock will vaporize. And we know these planets are made out of rock based on their bulk density. There's nothing else they could be made out of. So yes, by definition, these planets must have gas on their day side, but they probably don't have anything going on their night side. Their night side is probably a barren rock with no atmosphere whatsoever. And then anything more than this, we can't really say for sure yet because we don't have the data and our models are not good enough yet. But we're hoping that James Webb will tell us. Okay, so at this point, this is the point in my talk where I have to. It's 18, I got about 12 minutes, but I want to leave time for questions. Okay, we'll see how much of this I get through. So M-Earth, this is the last part. Mostly I just want to convince you that, that this has to do with hot planets. Okay, so M-Earths at face value are temperate terrestrial planets orbiting a red dwarf star. So these are the planets everyone gets excited about. They're like, yay, it's in the habitable zone. And you get articles in Nature and everyone's really stoked. Okay, but okay, and they're very common. Okay, that's all fine. Okay, the issue is, can these planets actually have oceans? Okay, they're in the habitable zone, sure, but do they actually have water at their surface? And then the question you should be asking yourself, given that the title of my talk was hot, atmospheres of hot exoplanets or hot atmospheres or something like that, what the hell does M-Earths have to do with hot planets? And the answer is that even though those planets are habitable now, and they're in the habitable zone of their star now, when their star was young, when the planet was young, they were receiving way more flux, all right? And so in the first, few 100 million years, the M dwarf host is going to be much brighter, okay, luminosity that can be, an order of magnitude higher than it is today. And the extreme ultraviolet luminosity, many orders of magnitude higher than it is today. And so that means that these atmospheres were hot and they were heavily irradiated with high energy radiation that in principle could have ripped apart molecules and basically sterilized these planets when they were young. So that's the big question. This is our worry with these M dwarfs, right? So this is a big thing we're going to try and answer with James Webb. But in the meantime, let's try and do some theory on this. So there have been a lot of works in the past looking at this deep water cycle on exoplanets, this notion that you can basically, water that's in the ocean gets subducted, it ends up in the mantle, it gets degassed via volcanism. And so you have this kind of deep water cycle. And then what my PhD student, Kevin Moore, has been looking at is, can you couple this deep water cycle with loss of water to space? Okay, and so this is what we call, sorry, one sec, let me go back to my presentation. There we go. Sorry, my computer was telling me I had to do something right now, which is unfortunate because I'm already doing something. Okay, so we call this the M-Earth Revival Project, right? So the idea is can you keep a planet orbiting a red dwarf habitable during the hard times by basically stuffing a bunch of water down in the mantle and the rocks, and then once the star chills out, you just burp up the water back to the surface. So that's the idea. The challenge is that during those early years, during those first few 100 million years, the surface of the planet is probably way hotter than it is now. And that's because the star was brighter, okay? And so it was giving off more flux. So probably these planets were in at least a runaway greenhouse state. And they might have had a magma ocean. They almost certainly had a puddle of magma at the surface, but they might have actually had a whole magma ocean. And so the point is that this brief hot stage of these planets essentially determines their long-term habitability, because the whole game is won and lost in these first few 100 million years. So even if you really only care about little green men and habitable exoplanets, you should worry about hot planets, because this hot planet, now is going to become the habitable planet of tomorrow. And so the question is, how quickly does it lose water? How well can it keep water hidden away in the magma ocean? Can it sequester some of that water down in the solid mantle? So this is ongoing work that hopefully will get submitted soon. Okay, so basically the answer to this question, do M-Earths hold on to their oceans? maybe, like we've got some possible geophysical mechanisms that might work. We kind of hope they can hold on to water. And this is another case where James Webb will tell us. So I've mentioned James Webb a couple times. As you all know, it's currently commissioning. The launch was amazingly successful. We are very excited. So just to give you one example of how James Webb might answer this question of, do these planets actually hold on to water? We might do transit spectroscopy. And so this is an example where we basically said, what does our Earth look like in a transit spectrum? And therefore, what might a habitable exoplanet look like in a transit spectrum? So this is work by another one of your fabulous undergrads, Dvani Doshi, who did this work with me mostly last summer as a paid intern, and then has somehow moonlighted doing this while taking classes, and the paper is now submitted to MNRAS. So she's another one of your superstar undergrad researchers. And so what Dvani did here was basically build an empirical spectrum, an empirical transit spectrum of the Earth, and then basically rescaled it for what it would look like for an exoplanet, and then made synthetic James Webb observations. And then in a separate part of the paper that I'm not showing here, actually did full spectral retrievals to see how much information she could extract out of all this. And so the basic punchline from this is that the particular thing she was looking at was stratospheric clouds, which is something I'm not going to go into right now, but it's a kind of a cloud that we were worried about for transit observations because they're clouds at high altitude. We see these on Earth every once in a while. And we were worried that if these occur on exoplanets, they might scuttle our transit observations. And so the good news is that they don't. So that's one of the punchlines from Dvani's paper. But the bad news is that this is still a freaking hard measurement, okay? And so what she's showing here is the result of pretending that every time TRAPPIST-1e transited its host star, we could just commandeer James Webb and look at it. And we did that for 5 years, because at the time that she wrote this, I think we still were being conservative about the mission lifetime for Webb. And so the point is this requires like 100 transits stacked together in order to start detecting features here that have to do with the molecules in the atmosphere, right? These features are what are going to tell us whether there's water vapor in the atmosphere of this planet. So this is hard. And so it turns out we've known for a while that this is going to be, more or less hard. And so some of us advocated, going back, I guess, 7 years now, that James Webb, this is a unique opportunity for James Webb. It's hard, but James Webb is the only thing that can try and study these M-Earths in the foreseeable future. Like, do these planets have atmospheres? Are they habitable? Are they inhabited? That's a bit of a stretch, but it's not physically impossible with Webb. And the problem is that it doesn't leave that much time to study other interesting exoplanets, of which, I've given you a couple of examples, these hot Jupiters and lava planets, but there's all sorts of water worlds and sub-Neptunes and this and that's and super puffs and there's a lot of interesting exoplanets out there that you might want to study. And James Webb, it's uniquely capable to go after these habitable ones that have a lot of sex appeal. And so the tax might favor that. And so that leads to Ariel, which is sort of the way to kind of clean up all the other planets, all the non-habitable ones. So Ariel is an approved ESA mission that will launch in 2029, or at least it's scheduled to launch in 2029. It's like a 1 meter primary mirror. So not that big, but it gets, kind of red to near to mid-infrared spectra for hundreds to thousands of planets. Okay, that's the goal. And so this is basically cleaning up all the hot Jupiters, all the kind of fluffier planets that have bigger atmospheres that are easier to detect. The idea is to go after all of them and do some good comparative planetology. Okay, I made it to my last slide. So I talked about what my research group has been doing. I didn't talk about Hubble, but we do some Hubble stuff too. I talked a lot about Spitzer. I skipped over the Kepler stuff. We've done some of that. James Webb, we're really stoked about, and Ariel, we're excited about and trying to work to get Canada involved in. And so with that, I will stop and answer any remaining questions you have. Thank you.
Okay, any questions? Please raise your hand. Neil.
Yeah, hi. So you mentioned about these emirates that might lose their oceans. And so just wondering, so for the Earth, I thought that, later on there was this like late heavy bombardment or something that then brought lots of water to the Earth. Could something similar happen for these emirates, that happen to lose their oceans?
Yeah. So you're referring to the thin late veneer, and that is less fashionable now than it was in the days when you and I learned about this.
Okay.
So basically, the dominant hypothesis now is that planets accrete their water at the same time as they accrete everything else. So you basically build a planet out of asteroids, and asteroids have some small percent water, and then you proceed to probably lose a bunch of that water during this early magma ocean phase. Or especially as the magma ocean is solidifying, essentially you're squeezing out. Magma oceans can hold just a bucket load of water, like many bucket loads of water. So a magma ocean can be almost 10% water by mass. So the magma is very happy to be very watery, but then as it solidifies, all the water gets concentrated in the magma and eventually just gets burped up to the surface. And if your star is going crazy with XUV, then you basically lose the water to space. So yeah, that's our current hypothesis, but this is still very much an area of active research. So yeah, absolutely. If you can invoke stuff falling on the planet later, you'd be fine. The problem is that this whole timescale is completely protracted compared to what we're used to in the solar system, right? In the solar system, the sun was a fully formed star, and then the planets form, and the planets all form within millions of years. Now we're talking about a process lasting hundreds of millions of years before the star chills out. And so the question is, at that point, probably the planetary system is very clean. There's not very many close calls and collisions. You don't expect a lot of rocks to fall into the planet at that point. So it's not, I think I have seen papers looking at this, but it's kind of a low probability move, I think.
Great, thanks.
James?
Thanks. This is sort of a background question, but is water what drives plate tectonics on the Earth? Is that sort of the current understanding?
It's not exactly what drives it, but it might be necessary for it. And there's a couple of reasons for this. The simplest one is just a viscosity thing. Is basically putting in homeopathic levels of water in the mantle reduces the viscosity by orders of magnitude. And so it helps basically lubricate the mantle, and it makes plate tectonics more easy. There's a second order sort of answer, which is that water also helps to create continental crust. So basically when you subduct hydrated basalts and you heat it up, this is some of the processes by which you can essentially create thick continental crust. And thick continental crust is necessary paradoxically for subduction. So the reason subduction is happening in the first place is that you have these thick continents and the ocean gets there and it kind of gets forced underneath. So it's a bit of a chicken and egg thing. Again, very much an area of active research. We literally don't know when plate tectonics started on Earth. There are estimates saying that it started halfway through the life of the Earth, so only 2 billion years ago. There are estimates saying it started sort of when Earth was still nascent. No one really knows. Our ability to predict this, much like magnetic fields, is dodgy at best. So yeah, we don't really know, but it seems most people think that water helps plate tectonics happen. Yeah.
Okay, thanks.
Other questions? Okay. All right. Well, thank you very much, Nick. It's a very good talk.
Thanks so much, Nick. That was very nice.
Thanks, everyone. Thanks for being here.